Example M4.1, the 50 kilogram crate shown rests on a horizontal surface for which the coefficient of kinetic friction is 0.3. If the crate is subjected to a 400 Newton towing force as shown, determine the velocity of the crate in 3 seconds starting from rest. So, the 3 steps that we went over in our module was to first draw out the free body diagram, because this will help us determine the unbalanced force that causes the crate to move, so that we can apply the equation of motion. And then, since we are supposed to determine the velocity of the crate in 3 seconds starting from rest, we have to apply the kinematic equation. So, as shown in the figure, we already determined the free body diagram, or constructed the free body diagram. So what's left is to draw out the kinetic diagram as well. Drawing out the kinetic diagram will also help us determine the direction of the acceleration. Okay, and so we see that since it's stated in our module that it's safe for us to assume the direction of the acceleration to go with the positive direction of the coordinate system, we are having the acceleration go to the right, okay, and that is 50a, alright, because from the equation of motion, m times a, okay, where m is the mass, which is 50 kilograms for this crate. Okay, so next we will apply the equation of motion. In this case, we are applying it to the x and y axes. Okay, so we have 400 cosine 30 minus 0.3 nc, okay, or the friction force is equal to 50a. So that 400 cosine 30 should be pretty self-explanatory at this point, okay, because that is it's inclined about 30 degrees from the horizontal, so the x component of this force will be 400 cosine 30. And for summation of forces in the y-axis, we have the normal force minus the weight, 490.5, plus 400 sine 30 equals 0. So solving simultaneously will yield 290.5 newtons and an acceleration of 5.185 meters per second squared. Having determined the acceleration, alright, we can then determine the velocity of the crate in 3 seconds starting from rest using the kinematic equations. Now, since the force is constant, it should follow that the acceleration is also constant. And since the acceleration is constant, we have to idealize this as a particle under constant acceleration. And we can use this equation right here. V is equal to V naught plus A times T. Alright? Now, since the particle is starting from rest, V naught is equal to 0. And your velocity after 3 seconds is 15.6 meters per second. Example M4.2, a 10 kilogram projectile is fired vertically upward from the ground with an initial velocity of 50 meters per second. Determine the maximum height to which it will travel if A, atmospheric resistance is neglected, and if atmospheric resistance is measured as 0.01 v squared Newton, where basically where it basically says that the atmospheric resistance is a function of the velocity, okay, where v is the speed of the projectile at any instant measured in meters per second. So it's the same thing as example M4.1. We will draw out the free body diagram, and then from that free body diagram determine the unbalanced force so that we can apply the equation of motion, and then apply the kinematic equation so that we can determine the maximum height, since we cannot determine the maximum height by the use of the equation of motion solely. So drawing out the free body diagram for part A, so we will be doing this in 2 parts. where atmospheric resistance is neglected, and then where atmospheric resistance is factored in. So for part A, we draw out the free body diagram shown here, where this is the particle, this is the free body diagram. So we only have weight coming down, which is 98.1 newtons, and that is from, okay, this weight is from the 10 kilograms times the gravity, which is 9.81 meters per second squared, and that is why that is 98.1 newtons. And you see here, acceleration is upward because we assumed we assumed it to be upward because of the guidelines in the module to assume that the acceleration of the particle will move in the positive direction of the coordinate system you chose. And in any case, it will give you, if it will give you a negative answer, we know to flip the direction. All right. So next, we apply the equation of motion, which in this case we are using z, right? Because z, or you can use y for that matter. It just so happens in this example we're using z for upward motion. Okay, so we have F is equal to ma, which is w, negative w, okay, because it's going down, equals 10a. And so you have an acceleration of 9.81 meters per second squared downward. Okay, this would have resulted in a negative answer, but I just because this would have been 9.81, negative 9.81 rather, equals a. So which just means that our direction that we assumed is wrong, and you can just flip the direction here. Okay, next you can apply the kinematic equation. So since the acceleration is constant, initial velocity is 50 meters per second, final velocity is 0 meters per second. It's 0 meters per second, the final velocity, because again, when you throw an object, allow me to draw, when you throw an object upwards, it stops momentarily and then it comes back down. Okay, so the velocity at this point is 0 meters per second. Okay, so its initial position already is, it's up to you, but we will take it as z equals 0 at this point. So this will be the datum line. So applying that, substituting those values into this equation here for a particle under constant acceleration, we will have a max height of 127 meters. Now, what if we move on to part B and factor in the atmospheric resistance? So the solution that we took will not differ in a sense that the process is the same, only that we will introduce another force. That's it. Just introduce another force. Okay, so this will add to your equation of motion here. Okay, so that's negative w minus fd, and so a will be a function of v, and you use this expression of a in terms of v in your kinematic equations. And because the acceleration is no longer constant, kinematic motion equations cannot be used, since we derive those equations on the basis of constant velocity or constant acceleration. Now, because of the introduction or the factoring in of the atmospheric resistance, your acceleration is now a function of the velocity, and as velocity increases or decreases, your acceleration will decrease as well. And so you have to apply the differential equations and integrate from those. Okay, so we have ATDZ, okay, or that's ADZ, or if you recall in your module, that is ADS, or the differential position is equal to VdV. We already discussed this in a previous module. If you need to refresh yourself, you can always go back to that module. In any case, let's move on. So plugging in the expression for A in terms of V here, and the V here, and then we find that this is a variable separable equation, so we can isolate variables Z and V, and so we can integrate from on the left side we have dz integrated from z sub 1 to z sub 2, and on the right side we have v over negative 0.001 v squared plus 9.81 dv, okay, integrated from v sub 1 to v sub 2, noting that z sub 1, or the initial position of z, is at 0, the final position of z is at h, or the maximum height. The initial velocity is 50 and the final velocity is 0. You plug in those values into this equation and carry out integration. You will arrive at an h of 114 meters. So the difference between the factoring in of atmospheric pressure and not factoring it in is approximately 13 meters. It may not seem as big of a number to you, but as a visualization, 13 meters is about 4 stories. So that's a four-story building. So that's a big difference. So you have to be careful when you're solving problems like this, and be careful if they want to include atmospheric resistance or not.